Okay, class, so now we're going to be starting a new unit and it's going to be titled Energy. And so at the basic level, we have the kinetic molecular theory. And this theory is just going to discuss how particles move at the molecular level. So to get used to that and to get ready for that, we're going to discuss a little bit about what kinetic molecular theory means. First of all, the kinetic actually just means, and you probably remember this from middle school, when you see KMT, it just means kinetic molecular theory. And it's mostly just motion, and then sometimes you're going to see motion in the way that it moves. At the molecular level, whenever you see this word, it just means in the word molecules. So when we apply the kinetic molecular theory, it mostly just means moving molecules. So if we just put these two together down here, you have moving molecules. And depending on the speed that the molecules are moving, will determine if we actually have a gas, a liquid, or a solid. So here's just a little snapshot of what molecules look like if they're just moving around constantly. They just, move at their own little pace, and depending on if they're a solid, liquid, or a gas, they'll move at different levels. This one would probably demonstrate more along the lines of a gas because they're moving pretty rapidly, and they're not having too many collisions with one another. It's probably getting to the steam going into the gas phase. So you probably remember this from middle school, but this is the kinetic energy formula. And the kinetic energy formula just states that you would just take 1/2 of the mass times the velocity squared. The mass in this case is always going to be in kilograms, and the velocity is going to be in meters per second. Now you may want to take a minute to jot this formula down into your notes just in case you do not have it. It's a good practice to make sure that you're taking notes off of my videos. So whenever we're looking at the kinetic theory, we have these pillars in which it stands on. Now, it's not always the case, but in a perfect world, this is what we take our kinetic theory from. First of all, the first part of the kinetic theory states that all molecules are made up of these small, hard spheres. Think of a bunch of billiard balls rolling around at one another. Sorry for that pop-up down there. So we're looking at the molecules are made up of these small hard spheres, and that is one determination of this kinetic theory. Now, another determination to see, what we're dealing with here is that gas molecules are always in constant random motion. Also, another one is that all collisions are elastic. Now, this doesn't mean that they're stretchy. It just simply means that energy is being transferred and that there's no energy being lost in this transfer. So just be careful with that word. So once again, elastic means without loss of energy. That if it's colliding, that it's transferring its energy in its moving forms. Another pillar of the kinetic theory deals with temperature being a measure of the average kinetic energy of molecules. And the last one here is that there's no attraction or repulsion between particles. Now, this isn't actually true. Of course, there is a little bit of attraction or repulsion between particles, but again, we're trying to apply the kinetic theory at a very basic level. Think of it as being in a vacuum without anything else being around it. This is what we're using for the kinetic theory. Otherwise, the calculations can get very long and abstract, and you can see those more whenever you get into AP Chem. Now this diagram, the Boltzmann distribution diagram, just helps us to understand, and we'll just make this a little bit bigger here and move this around a bit, just helps us to understand the different temperatures and the speed in which the molecules will be going. So this Boltzmann curve, it can seem a little bit confusing. So if you get a little bit lost along the way, just simply pause, rewind, go back. So this red little curve right here at 0 degrees Celsius, you can see it's up pretty high and the speed is not as much as that of 1,000 degrees Celsius. So the average here of these molecules moving at 0 degrees Celsius is in this range right up in here. If you were to look at this again, so looking at the curve, if you're up here on this higher end, this is where the majority of the particles lie at 0 degrees Celsius. The particles are not moving that fast, and this is an average of the particles. If you, as opposed to down here, you can see that they definitely have sped up. Here, again, it's not really going too fast. The energy is low at this point. So let's look over into this range where the green space is going to be. So once again, just make sure that you're understanding that the speed up in here isn't very high, but if we compare it to this green curve right here, notice how it's starting to speed up a little bit. So we have increased the temperature and the speed of the molecules has also increased. If you look at the temperature range right in here at this 2,000 degree mark, the speed is even faster and the energy is higher because we're just looking at the speed going along the x-axis here, and it's even faster here at this blue line. So mostly what we're trying to get you to understand is the faster, I should say, the temperature and the speed of the kinetic theory are actually interrelated. So let's just take a look at this little diagram up here. It seems a little bit chaotic, but if you look at the oxygen at 300 K right in here, and then right over here, you could see that at 300 K with the oxygen, the average speed is about 400 meters per second. If you take it and increase it to 400 Kelvin, then you notice that the average speed went up to 560 meters per second. So putting all of this information together, we're going to take a look at a little video. You might want to just jot this down in the future. It's a good website. It's the preparatorychemistry.com, and we're just going to show you how these little particles move along in a solid, liquid, or gas format. So let's just take a look here. Okay, so this first one, let's just get this all in order. Okay, you might want to pause this again, take some notes if you'd like, but this first one here is showing the solid. Notice how packed it is. It's tightly packed. The molecules, even though they're moving, they're not really going anywhere. They're tightly packed, they're squished together, and there's not a lot of room to move around. Notice this little solid dot here in the center, this little brown one. He doesn't move too far past where he's at the moment. So despite these continual changes, it's staying in that area. Now here is a solid that's actually moving, heating up quite a bit, so you can see that the particles are also moving up, and eventually it's going to go into the liquid phase. So let's think along the lines of, let's take a look. Particles in a liquid here are moving fast enough to break attractions. If you follow this darker movement, you can see we're now to liquid phase. They're sliding past one another, these molecules, and so it's just speeding up. So think along the lines of the phase change from ice going to a liquid, and now we would be heating it, and we're probably right at that vaporization area where it hasn't completely gone off to a gas yet. It's starting to move around. You're starting to see some gas bubbles floating off until you get to this diagram right here. Notice how the gases are moving faster. They're not colliding frequently with one another, and they're just kind of sliding past one another. They're not even really touching one another. Every once in a while they may bump into one another, but this is just showing you how fast, if you increase temperature, the movement of the particles also increases. So that's just another little view. Take a look at this at your leisure just to make sure that you're understanding the differences here between the kinetic theory with the solid, liquid, and gases. So as a wrap up here, just make sure that you're understanding that if you have a higher temperature, you'll have faster moving molecules and therefore more kinetic energy. So here's just one little last diagram I'd like to show you. Notice that as kinetic energy is increasing, we're going from a solid at low kinetic energy, moving to this barrier point, sliding past this barrier, going up into a liquid phase. And as we keep increasing kinetic energy by way of increasing temperature, we will go into this gaseous phase. And once again, notice how the particles are moving at a rapid speed and they're not as tightly held together with one another. So if we are increasing kinetic energy, we are also increasing our temperature, and you will. And our last diagram has to do with the phase changes. If you recall our physical changes, whenever we were applying heat or taking away heat, we would see these different phase changes. So make sure you write these down in your notes. We will be looking at these later on, but you've probably seen the solid go to gas in the form of dry ice in the past. If you go from a gas to solid, that's something called deposition, which we talk about later on this year and more in AP Chem. If you go from a solid to a liquid, then you are melting. And if you go backwards from liquid to solid, you're freezing. You've probably understand these from, middle school sciences, but from a gas to a liquid is condensation, and from a liquid to a gas is vaporization, sometimes also known as evaporation. So I hope that this information helped, and we will be applying these in our kinetics unit.